In this video, the introduction to the ChargeMol program is going to be displayed. Let's start by talking about the structure and methods of the ChargeMol program. Atoms in materials, AIM methods, use the information generated by quantum chemistry methods to compute properties such as net atomic charges, atomic spin moments, bond orders, and others. These atomistic descriptors serve us to gain conceptual understanding of materials, and they can also be used to construct force fields to use in classical atomistic simulations. AIM methods link quantum chemistry and atomistic simulations since they facilitate parametrization of force fields using automated methods from quantum chemistry. The ChargeMol program is a computational implementation of the standard atoms in materials framework, which includes methods to compute density-based AIM properties, orbital-based AIM properties, and a library of reference atoms. This video is going to focus on the blue highlighted sections. The isolated reference atoms library is necessary as it is used to do the charge partitioning. The charge partitioning results are a starting point for the spin partitioning, if needed, and bond order calculation. A separate video is going to be posted on the AIM polarizabilities, dispersion coefficients, and orbital-based AIM properties. The ChargeMol program partitions the material's electron and spin densities to get net atomic charges, atomic spin moments, and bond orders. It uses the latest methods to achieve high accuracy, applicability to a wide range of materials, sound theoretical basis set independence, and computational cost, scaling linearly with increasing number of atoms in the unit cell. This flow diagram summarizes the steps the ChargeMol program does to implement the DDEC6 method. The major parts are as follows. First, the input files are read. Then, charge partitioning is performed, followed by the spin partitioning, only for magnetic materials. And then, the bond orders analysis is performed. Lastly, other files are created related to the AIM radial moments. To download the program, visit ddec.sourceforge.net, linked in the description. Once there, click the green button to download the latest version of the ChargeMol code. Once completed, click to Show in Folder. Drag it or copy to a separate folder where you keep your programs. If you don't have one, we recommend creating one in your local disk C. In this case, the folder is called computer_programs_information. We then paste the zip file with the code and extract it. Upon extraction, we proceed to open WinSCP to transfer files from desktop to Linux cluster, followed by PuTTY to submit jobs. Access the folder where you extracted the ChargeMol date folder and navigate it until you find the atomic densities folder. We recommend creating a subdirectory under your home directory called bin. However, you can place them in any directory you choose. Go into Atomic Densities folder in your computer and open a file in a text editor to choose the transfer settings. In this case, we find ASCII characters, so we choose text. Now, we transfer the Atomic Densities folder, dragging the folder to the cluster bin. This process takes its time. You can also zip the file and unzip it once in the cluster. Go back again to your computer's directory and open the ChargeMol Fortran date folder. Source code Linux, source code date. We first need to transfer the compiled executable file called ChargeMol date Linux parallel, and to choose a transfer setting, we open it. Since it contains garbled characters, we choose binary transfer mode. Drag the file over to the cluster bin. To transfer the entire folder without having a copy of the executable file, we drag it out a folder up in our computer folder. Now we go back a folder and drag the source code date folder using the text transfer setting. Hit refresh and place the ChargeMol date Linux parallel inside the source code date folder. You can also leave it where it is, as it allows for a shorter path name when running the program. Also, we need to make sure the precompiled executable has the permission to run as such. For that, right-click and go to Properties. Then, in the Permissions section, mark the X. In most of the cases, this should be enough to run the program. At this point, you should try to run the program. However, if that doesn't work, you have to recompile the program, and this is the process you need to follow. In PuTTY, type module avail to see the list of modules available. Look for something called GNU, GFortran, or GCC. I found GNU. Then load this module by typing module load GNU, GCC, or a similar command. At this point, go to the cluster directory and allow for the compile serial or compile parallel text files to be executables under properties. Also, make sure to set run_interactive equals false in the module global parameters file. Then go back to PuTTY and type cd space followed by the path of the folder where the files to compile the program are. Make sure you have the // at the end of the path. Now, type // followed by the name of the file to compile. In my case, compile_parallel.txt. A shortcut in PuTTY is to write the first letter of the file and press tab on the keyboard to complete the name according to the file in the current directory. Wait for the compilation to finish. Now, let's talk about inputs. Generally, you need two types of inputs, the one generated by other programs and the one generated by you. There are two possibilities when generating input files by other programs. The input file containing information about the orbitals is a file with a WFX extension. Files storing the electron and spin density on a real space grid include the BASP files ACAR2, CHD-CAR, and PODCAR, cube files, and XSF files. As for the file generated by the user, you need the jobcontrol.txt file, in which you specify the analysis you want to perform on the system, as well as other important parameters and information about the system. Also, you need the batch submission script, in which the options for the program to run are specified. Keep in mind that the precise setup of the script file will vary between different Linux clusters. Now, for the input BASP files, the BASP files must be generated from a BASP run at fixed geometry. That is, use BASP keyword NSW equals 0. Any geometry optimization, if desired, must be done in separate and previous BASP calculation. The recommended real space grid setting is prick equals accurate, with an approximately 400 electrovolts cutoff. BASP keyword NCOT equals 400. Higher cutoffs may be used, but increase the computational cost without significantly changing the assigned atom in material properties. Create a new folder in a different directory. That is not where you have your programs. In my case, I created a folder under my documents called example_runs_Linux. If you don't have BASP input files, you can get some under examples to run. I'm going to use the lithium manganese oxide as example. Now, go to the other folder and notice there are different input files. ACAR0 contains the frozen core electron density. ACAR2 contains the valence electron density. CHD-CAR contains the smooth valence electron density for all materials and spin density only for magnetic materials. And PODCAR contains information about the number of frozen core electrons. Select and copy the ACAR2, CHD-CAR, and PODCAR files. ACAR0 is no longer used, as ChargeMol now uses its internally stored reference core densities, which are more accurate and reliable. Go back to the examples to run folder and copy the job control text file and paste it into your example runs Linux folder. Go back to the main folder and access example job submission scripts. Copy the comet_fortran_parallel.ch file and paste it under your example runs Linux folder and open it. This is the batch submission file. When setting it up, you need to specify the random access memory (RAM) requested, the queue name, the required computational time, and the requested number of computing cores. All the computing cores must be on the same compute node. The particular keywords for your Linux cluster may be slightly different from the keywords shown here, but the basic idea is the same. Then, use the command export space omp_num_threads to set the number of OpenMP threads that will be used. The next line calls the ChargeMol executable. Make sure to write the correct path where the executable is. Now, the number of OpenMP threads is equal to the number of logical threads per computing core multiplied by the computing cores used in Job. For example, one logical thread per computing core with 12 computing cores equals to 12 logical threads. In this case, set OMP_num_threads keyword to 12. If there are 2 logical threads per computing core with 12 computing cores, set OMP_num_threads keyword to 24. Open the job control text file. The periodicity along the first, second, and third direction needs to be set to true. For BASP files, it is not necessary to write the input file name, as ChargeMol looks for the BASP input files. The charge type DDEC6 is the recommended to use as it is the most accurate. Lastly, we need to include the net charge keyword. In this case, the system has a net charge of 0.0. For now, save the file and close it. Later, we need to change the directory path for the atomic densities. Now, navigate in your computer files until you get to the location of the newly created example with the input files. Open one of the BASP input files to check the transfer settings, and drag the folder to the new directory in your Linux cluster home. Mine is called chargemul_jobs. Then, open again the job_control text file and modify the path name to locate the atomic densities folder. In my case, it's in my/home/my username/bin/atomic_densities/. Now that the two types of input files are ready, we can run the ChargeMul program. Go to the PuTTY window and type the command to change directory, which is cd space and the path of the directory where you have the VASP example. Then, you can type ls to list all the files in the current directory. To submit a job, type sbatch space followed by the batch file name and hit enter to run. Then, a message giving you the job ID is going to appear if it was successfully submitted. You can check the status of the job by using the keywords qstat space -u space and your username. A message similar to this is going to appear. When the job is still running and a file is open in a text editor in WinSCP, an end of file character could be added to the files that are still being written, making any text added by the program after that invisible. The proper way to check a file when the job is still running is to drag the file you want to check to your local computer. Once there, you can open it and check how the job is progressing. You can do so for as many files as you want, as I just did here. When you are done checking the files, delete them, as to not confuse them with the final version of all output files when the job is done. Notice a new file appeared when I refreshed the Linux cluster directory. This means the NAX file is now complete, and the program is now working on the ASMs file to later work on the bond orders file. Now, the NAX file can be opened safely in WinSCP, just as you're going to be able to open the ASMs one as the bond orders file appears, and so on. Once the job is complete, PuTTY should not return anything after asking for the status of the job, as in here. Now, transfer back to your computer the output files that were created. I am using the Control key on the keyboard while selecting the files I want to transfer with the mouse. Drag them over to your computer, and now you should be able to see them on your folder you created for the input files. Open the file with a .output extension in a text editor. Scroll to the bottom of the file. When a job is completed, a message similar to this is going to appear. Let's now have a look at the net atomic charges file. In the first column, the atomic symbol appears, followed by the x, y, and z coordinates in angstroms. In the last column, we can see the result NAX. Upon scrolling down, we find a more detailed version, including a column for the atom number, plus the same information that we had above. In subsequent columns, additional output information can be found. Now, open the atomic spin moments output. This is only generated for magnetic materials. Following the same pattern as the NAX output file, we see the atomic symbol x, y, and z coordinates and the ASMs in the fourth column. Upon scrolling down, the parameters are found, followed by the same information as above, but with the atom's number. Open the bond orders output, and we find the same format, with the fourth column now being the sum of bond orders, SBO. Now, when scrolling down, we're going to find the specific bond orders contributing to the SBO of each atom in the unit cell. To better explain the output, here we show the reference unit cell in red with the unit vectors A0, B0, and C0, and the atom lithium number 1 inside it. This line tells us that lithium is bonded to the translated image of atom manganese number 10 in the unit cell with a unit vector of B-1 from the reference unit cell. and that a bond order of 0.002 was found. That is done for every atom that is connected to lithium number 1. Then, the SBO for lithium number 1 is the addition of all the bond orders. The process is repeated for as many atoms the unit cell has, in this case, up to atom oxygen 56. A different way to analyze the output is to look at it in a graphic format in YAML, which you can also get from sourceforge.net. Open the folder with the outputs and drag the NACS output to the YAML window. Upon opening, you're going to see the material in its unit cell, which you can rotate. Now, the YAML menu is in the lower right corner where the YAML text is. Click it and then click Open Console. You can also resize by scrolling up and down with your mouse. Let's now go to Display, then Label, and click Number to get the number of atoms to show. For better visualization, the color can be changed in the console using the command color labeled followed by the color. We see now that the labels have changed to yellow and are easier to read. Another important command is to show the results from the output files. For that, we use the command label %P. Now, the numbers reflect the NAC for each atom, and we can check it by clicking on an atom. We use the information on the console to look for that atom in the output file. We see that the NAC indeed coincide. Let's try the same now with the bond orders output. Now, I chose for the symbol to appear as a label, but once again, it is not distinguishable, so we need to change the color. Then, we display the SBO for the atoms. This number can be found here in the output. You can also find it in the first part of the file, although it is harder as you cannot see the atom number. We now focus on the input for WFX type files. As before, create a folder with the name of the example you want to run. Now, I'm going to paste my WFX input file. I'm also going to copy and paste the job control and batch files from the last example to this one. Open the job control input file to make the necessary changes. In this case, we delete the periodicity as it is not needed for WFX files, and proceed to write the correct path for the location of the atomic densities in your Linux cluster. Delete the net charge as it is contained in the input file itself. Now, it is necessary to add the keyword input file name. We then proceed to copy and paste the name of the WFX file and add the extension. We save the file and close it. Now, open the batch file and increase the limit on the total runtime of the job. As for WFX files, the density grids are generated by the ChargeMol program. Save it and close it. Essentially, the WFX files store all information the ChargeMol program needs to regenerate the molecular orbitals the program uses to make an electron density grid, and it allows ChargeMol to analyze the orbitals. The WFX file can be opened in a text editor, and it contains the Gaussian basis set specifications, nuclear positions, system or unit cell net charge, basis set coefficients for natural orbitals, and natural orbital occupancy. Go to WinSCP and transfer the folder where the input files for the new job are. Once done, access it. Go to PuTTY and change the directory to access the one you just transferred to your cluster. And submit the job with the sbatch command, followed by a blank space and the name of the batch file. After the job is submitted successfully, hit refresh and note the appearance of two output text files. Remember not to open such files in WinSCP when the job is still running. For that, you can use the qstat command. This process took longer compared to the VASP example. Once you know the process has finished, transfer the output files to your local computer. Outputs are now directly analyzed with YAML. First, the NAC output is analyzed. Notice that now the unit cell is not displayed. Another way to change the label color without the console is by going to YAML, Menu, Color, Labels, and choose the color you want. Then turn on the label display. Another useful command for the NACS file is the color partial charge, in which the atoms are colored based on the charge. Now we want to look at the results and use the labeled %p command. We see that the atoms information can also be found in the text file. Let's repeat the same now with the bond orders. Since this is a non-periodic system and the bonds are within the system, all atoms are in the reference unit cell. That is, all atoms are in the 000 unit cell. We look for C84 and find the SVO displayed in YAML. Now, we repeat the same process for the ASMs file. A shortcut in YAML is to press the up arrow key and the commands are going to be copied in the order they were used. Now the data displayed are the ASMs for each atom. A very common way to get an error message is demonstrated. I will copy the input files for the BASPE example in a different file. When opening the job control, I'm going to leave the directory for the atomic densities as it is and run the file. When opening the .output file and going to the end, we find a message similar to this. When this happens, output files are never going to be generated, as the program couldn't find the atomic densities file and quit. To fix this error, you have to specify the correct atomic densities directory path in the job control text file, as explained in the previous examples. For more information about the theory the program uses to calculate NACs, ASMs, and BOs, you can look at the past YouTube videos published. Stay tuned for more videos and tutorials.